Hello and welcome to Calculus 1 Integration. So what is integration or sum? Integration or sum is the reverse process of differentiation. It is the process to find areas, volumes, and other quantities. As an example, let's consider a curve fx, like fx equal x squared, where dx is a small step or distance underneath fx, in a way that y equal fx dx. That's the area of the rectangle right underneath that section of fx, where fx here, okay, is the height of the rectangle in this domain, which is bounded by x and x plus dx. So dx is a small step, or like the width of the rectangle, and fx is the height of the rectangle in this small section of the curve. So it is the area of a very small rectangle sitting right under the curve, which is equivalent to the area between the curve and the x-axis from x to x plus dx. This is x plus dx. dx is a small quantity that the parcel of the curve in that area appears to be a line, okay, a straight line of the rectangle. fx dx is the area of the curve in the dx domain. So to place it, or to say it in a different way, the integral is the limit of a sum according to Riemann, alright, where Riemann integral is defined by the following. It is the sum of all areas, small areas, defined by fxi, where xi is a point, like a coordinate on the x-axis. Fx is the height of that point, times delta x, where delta x is the step, and this is the sum when x goes to infinity to all the small areas between I equal 1 and I equal n. The interval AB is divided into n subintervals of equal distance. Delta x equal b minus a divided by n. xi is a point in the I subinterval, and fxi times delta x is the approximated area of the curve under that subinterval. So the integration is the sum of the areas underneath the curve, where dx is a fixed microstep that starts from the beginning of the first boundary of the domain to the end boundary. This sum adds up all the areas and results in the domain, result in the calculation of the overall area between the curve or function and the x-axis. Of course, in indefinite integral, you don't have boundaries. You are summing throughout all the definition domain of the function. So fx in such case is the sum, and c is the constant of integration. So integral x dx is equal large fx, which is the result of the integration, plus c. The integral is adding up all the products of fx dx, which are the respective areas underneath the curve for each step dx. There are no defined boundaries for which we are evaluating this area. That's why we call it an indefinite integral. As for the definite integration, a defined integral computes the accumulated value of areas, in this case, over an explicit and well-defined interval between two boundaries or two bounds. Like here, integral or sum from a to b of fx dx equal fb minus fa, or fx, instead of fx plus c, it is f of b, where you replace x by b, minus fa, where a and b in the example above are the boundaries of the integral. They are the two vertical lines x equal b that cut a part of the curve for which we are evaluating the area. Now, the derivative of an antiderivative gives you back the original function. So, if sum of fx dx equal f, capital Fx plus c, then fx prime, or the derivation of fx, would give you back the function lowercase fx, which is the one we summed up before. As an example, let's integrate x2 dx. So sum of x2 dx is equal x3 divided by 3 plus c. Okay, this is the power rule. When you integrate, you add up 1 to the power, then you divide by that added power. Okay, so x2 plus 1 over 2 plus 1, which gives you x3 divided by 3 plus c, which is the constant of integration. Therefore, the derivative of x3 divided by 3 would give you 3x2 divided by 3, or x2, which is the original function. Let's find the integral of y equal x2 between x equal minus 1 and x equal 1. Y equal x2 is the parabola equation that passes through the origin and cuts the y-axis at x equals 0. The formula for the integration of a powered x, or x to the power of n, is equal to x power n plus 1 divided by n plus 1. So for the indefinite integral, y is I equal integral of x2 dx equal x3 divided by 3 plus a constant. As for the definite integral, I equal sum between minus 1 and plus 1 of x2 dx equal x3 divided by 3 between plus 1 and minus 1 equals minus 1/3, alright, is equal to 2 divided by 3, or 2/3. Also, another way to get this area is to integrate from 0 to 1 of the function y equal x2 and multiply that by 2, since we have is an even function. Okay, it's symmetric according or in relation to the y-axis. Now these are the basic formulas for integration, which are the building blocks for solving an integral. Okay, you're gonna base your calculation on these formulas to find the solution for more complex equations. At first, we have integral of x to the power of n dx is equal to x to the power n plus 1 divided by n plus 1 plus c, of course, for n different to minus 1. Second, integral of 1 over x dx, which is also in another form, integral of du over u, where du is the derivative of u, of the denominator. So here u equal x, du equal 1. The derivative, okay, integration of du over u gives you ln u plus c, or in this case ln x plus c. Integral of ex dx is equal ex plus c. Integral of a to the x dx is equal to a to the power of x divided by ln a plus c. Integral sin x dx is equal minus cosine x. Integral cosine equals sine x, which is the opposite of the derivative, by the way. Integral of secant square x equal tan x plus c. Cosecant square x dx minus cotan x. Integral of secant x is equal secant x plus c, okay, etc. Here you have integral of 1 divided by square root of 1 minus x squared dx is equal to arc sinus of x plus c. Integral of 1 divided by 1 plus x squared is equal to tan minus 1 to the power minus 1, or arctan of x plus c. Integral of 1 divided by x, absolute value of x, square root of x squared minus 1 is secant to the power minus 1 x plus c. Also another forms that we might have not seen yet. So integral of a to the power of x dx is equal a to the power of x divided by ln a plus c. Integral of e to the power ax dx is equal 1 over a exponential ax plus c. abx, a to the power of bx, is equal to 1 divided by b ln a abx. Integral x ln x ln x dx is equal x ln x minus x plus c. Integral log base a x dx is equal x ln x minus x divided by ln a plus c. 1 over x dx ln x plus c, etc. Okay, 1 over ax, of course a, since it is a constant, okay, you take it outside and you have 1 over a ln x plus c. Okay, now let's start doing some practice exercises. At first we have I equal integral of 2 to the power, or 2x to the power of 3, 2x3 plus x plus 1 dx. Now the integral of a sum is equal to the sum of integrals. In other words, the integral of 2x3 plus x plus 1 is equal to integral 2x3 plus integral of x plus integral of 1 dx, each of them multiplied by dx. At first, we have, as we mentioned, the integral of a sum is the sum of integrals, which is equal to integral 2x3 dx plus integral of x dx plus integral of 1 dx. I is equal, okay, 2x3 dx. Now 2 is a constant, you remove it outside of the integral. x3 dx, the integral for that is x to the power of 4 divided by 4. Then integral x dx is x to the power of 1 plus 1 divided by 1 plus 1, which is x2 divided by 2 plus integral of 1 dx, or simply dx, x simply, okay, plus c, the constant for all of these parts, okay? And you can say c is equal c1 plus c2 plus c3, okay? For each integration you have a small constant, but globally c is the sum of all these constants. It is the constant of the entire integral, so to speak. So then I equal x4 divided by 2. We have reduced, we have factored the numerator and the denominator, plus x2 divided by 2 plus x plus c, integral of cosine 3x dx. So the formula for that, to solve that, is the following. You have integral of cosine ax dx, where a constant is equal to 1 divided by a, and the value of integration for cosine, which is sine, okay, ax, where of course the content or the angle of the cosine remains the same, only cosine changes to sine, plus c, which is the constant to be added. So integral of cosine 3x dx is equal to 1/3, so we divide by 3, which is the multiplicator on the inside, sine 3x plus c. Now, how did we get that? So let u equal gx, all right? You have du over dx equal g prime, or the derivative of gx. So du is equal to g prime x times dx, okay? So when we derive u, which is gx, according to dx, you get g prime x. So du is equal to g prime x, the derivative of gx, times dx. In this case, u is equal 3x, which is the angle of the cosine on the inside, right? So integral of fgx times g prime x dx is equal to integral of fu du, all right? This is called change of variable, where du is the derivative, okay, of 3x, correct? And the derivative of okay, we will swap, of course. So you have du equal g prime x dx. So dx that was multiplied here, we need to swap it by du over g prime x, or du over 3. So to give you an insight, okay, you have integral of cosine 3x, u equal 3x. Now du equal 3 dx, correct? Because du over dx equals 3. Du, the derivative of 3x according to dx, which is namely, technically you write it du over dx, or the derivation of u according to dx, is equal to 3. Then du is equal 3 times dx, which was in the denominator. We multiplied it here, okay? Then dx is equal to du divided by 3, correct? Hence, you have integral of cosine 3x is equal to 1/3 cosine u, which is cosine of 3x, times du, the derivative that we've gotten here, okay, du is equal to 3 dx. So we replace dx by du over 3, correct? So it is a replacement. Then integral of cosine 3x is equal 1/3 cosine u du, and you solve it for u. Integral of cosine u is equal to simply sine u, and you have the 1/3 on the outside. So it is equal to 1/3 sine u, or you replace back u by its original value, which is 3x. It is equal to 1/3 sine 3x plus c. I hope it is as simple as it can get. Integral of 1 divided by 2x plus 1 dx. This form seems to be familiar. It looks just like the form where we've seen you have du divided by u, and it produces a logarithm ln u plus c. Let's check it out. So integral of 1 divided by x, which is, as you see, the numerator is the derivative of the denominator, gives you back ln x plus c. Also, integral of 1 divided by ax, where a is a constant, dx, gives you 1 divided by a, which doesn't really matter. You can pull it outside of the integral. It is a constant. ln x plus c for a different to 0. Now, if you want, you can pause the video to try to solve it yourself. So let's start. We suppose u equal to x plus 1. So let u be equal to 2x plus 1. du would be 2 dx of the derivative according to x is equal to 2 dx. Then dx is equal to du divided by 2, which is the point. We need to replace dx by du and x by u, okay, or this entire form by u, which is called a change of variables. So dx becomes du divided by 2, and here in the denominator you have u. So it is equal to integral of du divided by 2, replacing dx in the numerator, divided by u, which is 2x plus 1, correct? Equal to this 1 over 2, you pull it outside, and you have 1/2 integral of du divided by u, which gives you ln u plus c multiplied by 1/2 on the outside. So equal 1 divided by 2 ln u plus c. Now we restore back the original value of u, which is 2x plus 1, so is equal to 1/2 ln 2x plus 1 plus c, which is the constant of integration. Another example for variable change or change of variables is integral of 6x multiplied by 3x2 plus 4 to the power of 4 dx. Of course, if you want, you can pause the video and try to solve it yourself, but in the meantime, let's move on. So if you let u be 3x2 plus 4, meaning u equals supposedly 3x squared plus 4, du is 6x, correct? 4 is a constant, it would become 0. And if you notice, okay, so du would be 6x dx, which you already have here. So you have, this is 6x and this is dx. You can plug them out immediately and swap them by du. And this would be u to the power of 4. So straightforward. So u equals 3x2 plus 4, du equals 6 dx. Also 6x equals du divided by dx. And yeah, we replace 6x by du divided by dx. Remember, here you have a dx on the outside, okay? Actually, the most easiest thing to do is to simply remove 6x dx, correct, and replace them by du. Okay, so you will have in the place of 6x dx du times u to the power of 4, because 3x2 plus 4 is u, okay, to the power of 4, so u power of 4. Integral is equal to integral of u4 du, or equal to u to the power of 5 divided by 5 plus c. Alright, so we came back to the power rule of integration, which is you add to the power 1 and you divide by the added power, correct? By the value of the power, which finally gives you 1/5 u to the power of 5. Remember, u is 3x2 plus 4 to the power of 5 plus c. Integration by parts. What do we mean by that? You have a rule in the integral, which is when you have a u function multiplied by dv, you can break it down into u times v minus integral of v du. Alright? So you have two functions, u and v. You can break them down into u, and here you suppose that the first one is u, the other one is dv. It is equal to, the integral is equal to u times v minus integral of v du. Of course, dv and du are the derivatives of, respectively, the functions v and u. U is a function you differentiate, and dv is the function you integrate. So you get the derivative of u. As for dv, you get the v. In other words, you suppose a part, or the second function which is multiplied by u, is dv. So you integrate it to become v. Okay, you integrate whatever function you have v here to become v. Then du and v are respectively the derivative and integral of u and dv. So du is the derivative of u and v is the integral of dv. So this would be an ordinary function that you supposed to be dv, and you integrate to become v, which is another form. To get a clear insight, we're going to work on a sample or an example, which is integral of x e to x dx. Of course, you can try at it yourself and pause the video. Now, after that, let's go at it. So let x be u and dv equal e to x. So let u is equal to be equal to x. Du is equal 1 dx, which is the derivative of x. dv equal e to x, so v equal integral e to x dx, which is equal to 1/2 e to x. Integral x e to x dx is integral to u dv. U is x, dv is equal to e to x, equal to uv, that's the formula for the integration by parts, equal uv minus integral of v du. So uv is x times v is 1/2 e to x minus integral of v du, or minus 1/2 e to x times dx. So it is equal to 1/2 x e to x, which is uv, minus integral of v du, or 1/2 e to x times du, or 1 dx. Let's expand. It is equal to 1/2 x e to x minus 1/4, which is the integral of e to x 1/2 multiplied by 1/2, so minus 1/4 e to x plus c, which is the constant of integration. Now, when applying integration by parts, we need to use what is called the Eilate rule. It is an acronym, so we can memorize which are the functions that need to be taken as u in preference. So we need to take them in the following order of preference. I is the inverse trigonometric functions like tan minus 1x or arc sinus x. These are the inverse functions. That's first. Then the logarithmic functions such as ln x. Then the algebraic functions, which are x and x2. Then trigonometric functions such as sinus x and cosine x. Finally, the exponential functions, e.g. ex and 2 to the power of x. As you notice in the previous example, we chose u as being x, correct? So it was in preference of e to x, which came after in the preference. So this is how you choose u from the function that comes first in this list for easier integration. Another example for the change of variables. So you have integral of 2x divided by x2 plus 1 dx. You can pause the video, of course, and try to work on it yourself. In the meantime, so let u be equal to x2 plus 1. Let us notice something. So if u is equal to x2 plus 1, then du is equal to 2x dx, which is the numerator times dx. So you can remove these two products and replace them immediately by du, while the denominator would be u. So this will have a form of integral du divided by u, which is ln u plus c. As simple as that. So I, which is the integral, is equal to integral du divided by u is equal to ln u plus c, u in absolute value, which is, in other words, ln x2 plus 1 plus c. Integral of square root of 4 minus x2 dx. Here what you have is a form of a circle, all right? So the circle's equation is, as a review, okay, x2 plus y2 is equal r2, where r is the radius of the circle, and of course x and y, this is the equation of the circle, x2 plus y2 or x squared plus y squared is equal to r squared, r being the radius. In this case, if you change r2 and x2, or if you move x2 to the right handle of the equation, you get y2 is equal to r2 r squared minus x squared. If you notice, r here is equal to 2, which is 2 squared gives you 4. So y is equal to square root of r squared minus x squared. Now, of course, here the center is the origin for the circle, because the original equation of a circle is x minus a squared plus y minus b squared is equal to r squared, where the center of the circle is CAB. It has x equal a and y equal b. These are the coordinates of the center of that circle. Since a and b are 0, then the center for that circle is the origin, and thus the equation for that circle is x2 plus y2 is equal r squared, or more definitely x plus y squared is equal to 4. This is where we've gotten this equation. In such case, you need to replace x by something else in order to be able to solve this equation. Okay, what is convenient is to replace x by sin theta. Okay, sinus theta. So let's at first erase all ink. Okay, then go back to the laser point. So again, this is an equation of a circle with radius 2. You have y equal square root of 4 minus x2. Okay, so we need to change the variable using x is equal r sine theta, where r is equal to the radius, which is 2. These are the polar coordinates, by the way. Then x is equal to 2 sine theta. So let us change these values. So you have I equal to integral of square root 4 minus x squared, which is 4 sine square theta d theta. Okay, now 4, it can be factored out, okay, which is it multiplies both 1 and minus sin square theta. Okay, square root of 4 is 2. You bring it outside of the equation of the integral. Then square root of 1 minus sine square theta is simply cosine square theta, correct? Because cosine square theta plus sine square theta gives you 1. So equal to integral square root of cosine square theta d theta, which is 2 integral cosine theta d theta is equal to 2 sine theta plus c. To be more accurate, we're going to redo the previous example. Now, actually, when you move to polar coordinates, you replace x by r cosine theta and y by r sine theta, not the other way around. This is how you actually do it. All right, so what we're going to do here is replacing x by r cosine theta and redo the calculation or the example all over again. So again, this is an equation of a circle with radius 2. are equal to, which is 2 squared, that gives you 4. And this is how we got that. The original equation is x2 plus y2, or x plus y squared, is equal to 4, which gives you y equal to square root of 4 minus x2. Again, 4 is the radius square. Also, as a side note, you have the center, the coordinates of the center of this circle are 0, because the original equation is x minus a squared plus y minus b squared, where a and b are the coordinates of the center of the circle. Here the circle is centered at the origin of the axis. So we need to change the variable using x equal r cosine theta, which gives us x equal 2 cosine theta, because r is 2, which is 2 squared. This is what gave you 4. Okay, so r equal 2. I equal integral of square root of 4 minus 4 cosine square theta, which is the x square, times d theta. 4, you can factor it out, and the square root of 4 gives you 2. So this accounts for I equal 2 integral of square root of 1 minus 1 times cosine square theta d theta. 1 minus cosine square theta is sine square theta. So I equal 2 integral square root of sine square theta d theta, which is integral of sine theta, okay, which is I equal 2 integral sine theta d theta, or 2 cosine theta plus c. That's the final answer. Integral of dx divided by x times square root of ln x. Of course, you can try at it yourself and pause the video, but let's move on ourselves. Once you're done trying, here's the solution for that. Let's say that u is equal to ln x. So du would be 1 over x dx, correct? So when u is equal to ln x, du is equal to 1 over x dx. If you look at the integral, we already have 1 over x dx. So this altogether can be replaced by du. And in the denominator, you have square root of u, which is ln x. So I equal, and we broke it down to make it more simple and more visible, I equal integral of 1 over x dx, which is du, multiplied by 1 divided by the square root of ln x, or square root of u. So I equal integral of du divided by square root of u, and the square root of u is also written as u to the power of 1/2. You move it to the numerator, it becomes, you flip the sign. It becomes u to the power of minus 1/2 du, which is, the result for that is equal to u to the power minus 1/2 plus 1, because you always add to the power plus 1, and then you divide the entire power in the denominator. So u to the power minus 1/2 plus 1 divided by minus 1/2 plus 1, or u to the power divided by 1/2 equal to square root of u plus c, which is, you replace back u by ln x, which is equal to 2 square root ln x plus c. Now this one is a tricky exercise that involves multiple steps. At first you have the integration by parts, then you have a change of variables. Let's check it out. So at first you have sine ex, and you have the other part e to x. Okay, so let u be at first e to the power of x. Let's check it out. If u is equal e to the power of x, then du would be equal to dx. Okay, then you have the second part is, okay, so I is right now u sine u, okay, which is, you have e to the power of 2x has been divided by ex. Let's break it down. So again, you have u is equal e to the power of x, so du is equal to ex dx, then dx is equal to du divided by ex, correct? So you swap dx by du divided by ex. and you have e to x in the numerator. So when you divide e to x by ex, what is left is ex, which is u, multiplied by sine of ex, which is also u. So this is equal to integral of u sine u times du. Now the second step is replacing u and sine u by another u, which is, you know, uv. Integral of u dv is equal uv minus integral of v du. This is what we're talking about, except the next u would be a different u. It has nothing to do with the lowercase u that you have here. All right, so let capital U be lowercase u. Then du is equal to 1, correct? Then dv equal sine u. So v is equal to integral of sine u, which is minus cosine u. Thus, I equal uv minus integral of v du. Du is 1 times du lowercase. So, I is equal to uv multiply u by v. Capital U is equal to lowercase u times v, which is u minus cosine u, or minus u cosine u, minus v du, or v is minus cosine u, times du, or 1 du, correct? 1 times du, which is equal to, we need to, continue it. Okay, so minus u cosine u, and plus integral of cosine u, which is simply minus sine, or which is simply plus sine u. So the integral is equal to minus u cosine u plus sine u, or ex times cosine ex plus sine ex. So again, I equal uv minus integral of v du. I equal minus u cosine u minus integral of minus cosine u times 1 du, or minus u cosine u plus integral of cosine u du, which is sine u, correct? So minus u cosine u plus sine u plus c. You replace back u by its original value. So I equal minus ex, e to the power of x, times cosine ex plus sine ex plus c. I know that it's a little bit intricate, but you can work on it and, you know, become very good at it. It needs a little bit of practice, but it is straightforward. Integration by fraction. Now this is another form of integration, another model, where we need to break down the fraction into multiple fractions. All right, here's how we do it. As you notice, you have a common denominator, or like something that we can factor in the denominator to make it more simple. Okay, so you have integral of 2x2 plus 3x plus 1 divided by x3 plus x dx, where x you can take it out to multiply it by x2 plus 1. So you have 2x2 plus 3x plus 1 divided by, you take out 1x and you multiply it by x2 plus 1, is equal to 1 divided by x, that's the first part, plus bx plus c divided by x2 plus 1, which is the second part. What we need to do is to find a, b, and c, okay, the values of these three numbers. And here's how we're going to do it. Okay, so you need to expand. Let me show you how. All right, here you need to multiply by x2 plus 1, okay? And in the second part, you need to multiply by x, so as to have the same denominator to the left, correct? So here you have x times x2 plus 1. Then to the right you have a divided by x plus bx plus c, that's the form of the second part, divided by x2 plus 1. So we need to multiply a by x2 plus 1 and bx plus c by x, so as to have the same denominator, which is x times x2 plus 1, as the left part of the equation, correct? So a times x2 plus 1 divided by x times x2 plus 1 plus x times bx plus c. Now, so you get, okay, forget about the denominator, it factors out, okay, it is the same for all. you have 2x2 plus 3x plus 1 is equal to ax2 plus a plus bx square plus cx, correct? Right, so all that is multiplied by x2 is equal to 2x2, correct? This is how it works. Now, everything that is multiplied by x is equal to 3x. And finally, everything that is a constant is equal to 1. This is the constant part of the equation. So, you have ax2 plus bx2 is equal to 2x2. Then, cx is equal to 3x, correct? Then finally, a is equal to 1 because it is a constant. So far you have a equal 1, c equals 3 because you can factor out x, and ax2 plus bx2 is equal to x2. We already have a, so you can get b, okay? Because a is equal to 1, then b is equal to 2 minus 1, which is also 1. So c equals 3, a equal 1, then b equal also 1. You have a equal 1, b equal 1, c equal 3, and you can replace them here in this equation that we have simplified. Okay, so again, you have a equal 1, b equal 1, c equals 3. It is equal to, this equation is equal to 1 divided by x plus bx divided by x2 plus 1, which is b equal 1. So plus x divided by x2 plus 1 plus c, which is 3 divided by x2 plus 1. And we integrate this equation here, which is the equivalent of what we found here, okay? So 1 divided by x divided by x2 plus 1 plus 3 divided by x2 plus 1 is the simplified form of 2x2 plus 3x plus 1 x divided by the times x2 plus 1. So I equal integral of 1 divided by x plus x divided by x2 plus 1 plus 3 divided by x2 plus 1. Now, the most complicated part is the middle one, which is x divided by x2 plus 1. Let us find the integral of this fraction, okay? This part of the entire equation. So, let u be equal to x2 plus 1. du is equal to 2x dx, correct? So du over 2 is equal to x dx, which is here. That's x dx, correct? So that's the first one. And you get 1/2, okay, du, which is x dx, as we mentioned, it is equal to du. So du divided by 2, and the denominator is u, okay? So it is 1/2 du over u, which is ln u plus c, by the way. I is equal to 1, integral of 1 over x is ln x. That's du over u, correct? The derivative of x is 1. So integral of 1 divided by x is ln x plus 1/2, which is, you know, x is du over 2, and divided by u, so it is 1/2 ln u, which is x2 plus 1, plus, now here, if you go back to the formulas, of course 3, you put it to the outside, the integral of 1 divided by x2 plus 1 is actually arctan of x, okay? So 1 divided by x2 plus 1, the integral for that is arctan of x, or 10 to the power minus 1 of x, and 3 is a constant, it doesn't matter, you multiply it, so it gives you plus 310 to the power minus 1 x plus c. Volume calculation by disk washer method and through integration. Actually, in volume calculation we have two main methods. The first one is by disk or washer method. The second one is by shell method. We're gonna start with the disk or washer method. So what is it actually about? Imagine a curve that is bound between 2 points A and B and enclosing an area, which is the area between that curve and the x-axis. So what would be the volume of the solid created when this curve revolves around x-axis in this way, as you see it, okay? So the way that we're going to evaluate the volume is by considering each section of the function f(x). Actually, we slice the function f(x) into small parts. each part, when it revolves about or around the x-axis, it creates a disk, okay? And the area for that disk would be the x, which is the thickness of the disk, times fx, which is the radius of the function. And as you sum up all the areas of all the disks throughout the function, as you add up these disks together, you get the volume of the entire solid, which is bound, of course, again between A and B. So it is the sum of all areas for all the disks created by the function as it revolves around the x-axis. At each point, you have a disk being created, and instead of a point, you have the x, which is like a section or a small section that is the thickness of the disk. So the formula for that would be just like the area is pi r square. Here, instead of r, you have the function fx squared according, and of course multiplied by the x, which is the thickness of that disk. So the disk quotient method consists of slicing the function fx into circular disks. Each disk has a thickness dx and a radius fx. Revolution around the x-axis. So we're still in the volume calculation using the disk quotient method. Again, the volume is given by pi multiplied by the sum of all areas of the areas of all sectional disks, okay, multiplied by the x, which is the thickness of each section of each disk, rx being of course the radius at each point, okay, for the disk. So because you have at each point on the curve a different disk with a different radius, so we're adding up all the areas of the sectional disks that give you eventually the entire volume of the solid, of course bounded by two frontiers, two boundaries between A and B. Again, pi multiplied by the sum of rx square, just like pi r square gives you the area of a disk. Here, instead of a simple radius, you have a radius that is changing throughout the curve, and at each point you are getting the area of the disk multiplied by the x that gives you the volume of the disk. As you sum it up, you get the entire volume for the solid. Here it is when it's around the x, okay, when it's the volume revolving around the x-axis, you get evaluate the integral, okay, about the x-axis by multiplying by the x, okay. But when we are revolving the solid around the y-axis, you need to integrate in respect of y, the y-axis, or dy. So let's say you have y equal x2, you need to convert y equal x2 to x equal square root of y dy, and this is how you get the volume of that same function but revolving around the y-axis. So let's start with an example. The volume, we want to get the volume of the function y equal e to the power minus x from x equals 0 to x equal 1, okay, revolving around the x-axis. So this would be an image of what that volume would look like. This is exponential minus x, which is the inverted y equal x, by the way. Y equal x would be like this, and we are getting the volume from x equals 0, which is here, by the way. This is x equals 0 all the way to x equal 1. So v equal, applying the formula, pi times sum from 0 to 1 of fx squared dx, or rx squared dx. Rx here is equal to e to the power minus x square dx. So v equal pi sum from 0 to 1 of fx, or rx to be more accurate, square dx is equal to pi sum from 0 to 1 of e to the power of minus 2x, which is e minus x square dx, equal to pi multiplied by minus 1/2 That's the result of the integral. E to the power minus 2x between 1 and 0. Alright, equal to minus pi times 1 divided by 2 e to the power minus 2 minus 1. Okay, you replace x by 1, so you have minus pi 1 half e minus 2 minus 1, which is pi over 2. Okay, we like multiplied by minus to remove the negative sign here. V equal pi divided by 2 of multiplied by 1 minus 1 divided by e squared, of course, cubic units, if you will. Okay, that is the volume of y equal e minus x revolving around the x-axis between 0 and 1. Another example, let's get the volume of the region which is located under, or an area, if you will. Okay, region area located under y equal 2x minus x squared and spanning from x equals 0 and x equal 2, revolving around the x-axis. So here you have a curve which is 2x minus x squared, and we need the volume of that curve revolving, of course, of the area under the curve, revolving, if you will, around the x-axis between x equals 0 and x equal 2. So how do we get that? You have I equal integral between 0 and 2 y squared dx. Here it's not the volume, okay? We're gonna multiply by pi at the end. Here we are evaluating the integral of y squared dx at first, and then after that we will multiply by pi when once we are done with this calculation. Alright, so sum between 0 and 2 y squared dx equals sum between 0 and 2 2x minus x squared dx, okay, which is equal to, let's expand it, sum from 0 to 2 of 4x squared minus 4x to the power of 3 plus x to the power of 4 dx. Now you can simply calculate this integral, okay? So you have 4 times x squared integrated is equal to x3 divided by 3, of course, multiplied by 4, which is on the outside, minus 4x times 4 divided by 4, because x3, the integral is x4 divided by 4, plus x4 integrated gives you x to the power of 5 divided by 5, between 2 and 0, which is equal to 4x3 divided by 3 minus x4 plus x5 divided by 5 between 2 and 0, and you simply replace x by 2 because for 0 you have the entire thing annihilated, okay? So equal to, I've replaced x by 2, and you get eventually, if you evaluate it, 16 divided by 15, then the volume is equal to pi multiplied by the integral, pi multiplied by I, which is equal to pi times 16 over 15. That's the volume of the solid. Volume of a solid formed by the revolution of a region enclosed between two curves, capital Rx and lowercase rx. Rx, bigger Rx being the outer radius, the outer shell, if you will, and lowercase rx being the inner radius, which is the one, if you will, between the x-axis and the function rx, okay? And the second function, which is the lowercase rx. Capital Rx is the one from the smaller or the other function to the upper radius, to the upper or outer shell, okay, to the outer radius. So again, to wrap it up, you have the volume of the area revolving around the x-axis that is formed, or the region rather, that is formed between two curves, Rx being capital Rx or the outer radius, lowercase rx being the inner radius, which is the one closest to the x-axis, is given by V equal sum from A to B Rx square minus lowercase rx square times dx. volume of region between square root of x and x divided by 2 from x equals 0 and to x equals 4 around the x-axis. As you notice, y equals square root of x is capital Rx because it is the curved one. It is the one sitting above the line, which is of equation y equal x divided by 2 or lower Rx. And these two intersect at 2 points, which are at x equals 0 and x equals 4, which are the correct boundaries between these two curves. So we want to find the volume formed by the rotation of this region enclosed by these two curves around the x-axis. So capital Rx equals square root x, lowercase rx equal x divided by 2. Then the volume is given by pi integral between 0 and 4 r square x minus lower case r square x, which is the line, dx equal integral between 0 and 4 square root of x square minus x divided by 2 square dx equal sum from 0 to 4 square root x square give us x minus x2 divided by 4 dx. So I equal x2 divided by 2 minus x3 divided by 12. We've integrated here, so x2 divided by 2, and the second part is minus x3 over 3 times 4. This is where 12 comes from, equal 16 divided by 2 minus 64 divided by 12. Simply placing 4 here because for 0 it annihilates everything, which is equal to 8 minus 16 divided by 3 or 8 divided by 3. Then you multiply it by pi, you get the volume. So V equal pi times this entire value here, or pi multiplied by I. So V equal 1/3 times pi. That's the volume for the solid formed by the revolution of the area between these two curves. Now let's talk about the volume calculation using the shell method. So imagine a point. That point is being rotated around an axis from a distance of r. This point is dripping ink. As it rotates, it will trace a circle of radius r and circumference of 2 pi r. Okay? Now, instead of a point, imagine a section area like that between a curve y equal x2 and the x-axis. Okay, so the shell method consists of rotating that area with a rotation circumference of 2 pi r. But r this time is a function rx instead of, a simple radius, which is the height of the curve at each point. And x is the length, okay? xrx is the area of that curve. Let's look at it in a different or from a different perspective, okay? So y equal, let's say, 8 times x minus 1 square times x minus 2 square. Okay, this is the function here. Okay, that is defined from 1 to 2. Okay, this is where it cuts the x-axis. All right, so if you imagine revolving that area around the y-axis, okay, what you get is this volume of the solid here, which consists of this area. Imagine it rotating around the y-axis and like smudging as it rotates and filling an entire volume. This is what we're talking about. So the formula is for an area revolving around the y-axis, V equal 2 pi, and instead of r, you have the area, which is the sum here in this case from 1 to 2, or integral from 1 to 2, x, this is the x, multiplied by fx, okay, which is the height of the square, times dx, okay, times dx. That's, we are getting the area of this section and revolving it around the y-axis. So let's evaluate the volume for this function. You have at first y equal 8 times x minus 1 square times x minus 2 square. The volume is equal to 2 pi times integral from 1 to 2 x fx. Okay, now for the 8, it is a constant, so you can move it to the outside. We multiplied by 2 pi, so you get 16 pi on the outside, and then we process x. So v equals 16 pi integral from 1 to 2 x times fx dx. Fx is x minus 1 square times x minus 2 square, and you expand both products. So x minus 1 square is x2 minus 2x plus 1, x minus 2 square is x2 minus 4x plus 4 dx, and you simply multiply them together. So v equals 16 pi integral from 1 to 2 x times x4 minus 4x3 plus 4x2 minus 2x3. I multiplied these two together. Okay, this is how we expanded them. Times at the end dx, then you multiply by x from the outside, so you get 16 pi integral from 1 to 2 x times x4 minus 6x3 plus 13x2 minus 12x plus 4 dx. Okay, so eventually you get x6 divided by 6. Yeah, so once we are done, so you expand, you get, or you solve the integral. So x5, integral of x5 is x6 divided by 6 minus 6x5 divided by 5. Remember here it is x times minus 6x3, so it is minus 6x4, okay, plus 13x4 divided by 4, here it is 13x3, minus 12x3 divided by 3 plus 4x integrated, so 4x2 divided by 2, between 2 and 1, and you get the final result is 16 over 20 pi, or 4 divided by 5 pi. That's the volume for this solid. Volume of the region between x squared and square root of x from x equals 0 to x equal 1 around the y-axis. At first we're going to use the shell method. Now the upper radius, according to this plot, is the square root of x. The lower radius is lowercase rx equal x squared. Okay, so the upper radius is square root of x, the lower one is x squared. And as you notice, the two intersection points between the two curves, between both of the curves, are at x equals 0 and x equal 1 respectively, just as it is displayed within this image, just like the boundaries of this integral. So the volume of the solid when this region area revolves around the y-axis is equal to 2 pi integral from 0 to 1 x times capital Rx minus lowercase rx dx, equal 2 pi integral from 0 to 1 x multiplied by square root of x minus x squared dx, equal 2 pi integral between 0 and 1 x root x minus x3 dx. So it is equal to 2 pi. This is actually x to the power of 3 divided by 2. So the integral for that is x3 divided by 2 plus 1 divided by 3 over 2 plus 1, minus the integral for x3 is x4 divided by 4. Then you replace the x's by 1 because for 0 they become 0. So v equal 2 pi x2 square root of x divided by 5 divided by 2 minus x4 divided by 4 between 1 and 0. We replace x by 1. The volume is equal to 2 pi times 2 divided by 5, which is this quantity, minus 1 divided by 4, equal 2 pi multiplied by 8 minus 5 divided by 20, which is 3 over 10 pi. Alright, now let's work it using the disk or washer method and try to obtain the same value, because it makes sense. We should obtain the same volume using both methods. Obtaining the volume of the region between square root of x and x squared, this enclosed area here, as it rotates around the y-axis, we want to obtain the volume of the same solid just like previously, using this time the disk or washer method. Okay, the formula for that is v equal pi times integral from 0 to 1 ry squared minus lowercase ry squared dy. Here, since we are revolving around the y-axis, we need to change from the x domain to the y domain. Okay, we need to integrate in relation to y, to dy. The formula again is integral between 0 and 1 ry square minus lowercase ry square. Now we flipped the domain, so rx is equal square root x dx. We need to get the x in relation to y. Okay, ry, not rx, and that's lowercase, you're gonna see y, is equal to y squared dy. In other words, here's how we did it. Y equal square root of x, correct? We want to check what is x in respect to y, so we elevate both of them to the power of 2, then x becomes equal to y squared. Okay, this is how we obtained ry. We had at first y, the value of y in respect of x. We needed the value of x in respect of y, so we flipped everything around. The same thing for rx, so lowercase rx is equal to y equal x2, then capital ry is equal to x, which is equal, okay, so you have x2 equal y, so x equal square root of y dy. Okay, and now you have ry on the top, capital ry on the top, which is this one, and lowercase ry at the bottom. Okay, so we have, like, you have the graph flipped over. Okay, rx equal x2 was at the bottom, okay, but lowercase ry, which is this one, has become at the bottom x equal y squared, okay, which is the former root x, okay, it became at the bottom. We flipped around the interval. We need to take note of that. The outer radius is square root of y, which is capital ry, or the formerly lowercase rx. So this is the outer radius right now, square root of y, and the inner radius is y squared, which is used to be capital Rx. Okay, this is the inner radius. So you follow by the newly obtained equations. Okay, when we flipped x and y. Okay, when we got x in relation to y, you flip everything around. So square root of y has become the outer radius and y squared is the inner radius. Let's obtain the volume. So v equal pi integral from 0 to 1 square root of y square minus y square square dy. Here we are integrating in respect of y again. Okay, that's why you have the integration is according to the y variable and the differentiator is dy, no longer dx, because we are revolving around the y axis. So v equal pi integral from 0 to 1 square root of y square is equal to y minus y square square is equal to y for dy. V equal pi multiplied by, okay, let's integrate y square divided by 2 minus y5 divided by 5 between 1 and 0, which is pi multiplied by 5 minus 2, okay, which is this one. 10 divided by 2 is 5, 10 divided by 5 is 2, so it is pi times 5 minus 2 divided by 10, which is 3 over 10 pi, the same answer that we've gotten using the shell method. So that's it. We did both methods using, like, we calculated the volume using the disclosure method and the shell method. We obtained the same result. A new section, arc length calculation using first degree integral. So let's say you have a small chunk, a very small parcel of an entire curve that is defined between x and x plus dx. So dx is this width here, the width of, if you want, the interval right beneath this small parcel of a curve, and dy is the height of this interval. Okay, now if we consider this small curve, because on a very tiny interval it's no longer an arc but a line, the length of this small line according to Pythagoras theorem would be small l squared is equal to dx squared plus dy squared. L would be equal to square root of dx squared plus dy squared. Let's divide by dx squared inside, which is a differentiation of small l in respect of dx. In such case, you have l equal square root of dx squared divided by dx squared plus dy squared divided by dx squared. You factor it out, so it becomes square root of 1 plus dy over dx squared. Now, what is dy divided by dx? That is tan alpha. That's the slope. In other words, it is the derivative of fx or y equal fx in respect to x. You can rewrite it equal to square root of 1 plus f prime or the derivative of f to x squared. This is only the length of small l, or the length of this parcel, but this parcel is just a small fragment of the entire curve. So to get the total length of the curve, we need to integrate this entire equation throughout the entire domain where we desire to measure the total arc length of that curve, which is defined from a to b, where a and b are the boundaries of this integral. L equal integral from a to b square root of 1 plus dy over dx squared dx is equal to also another form for that, integral from a to b or sum from a to b square root of 1 plus f prime x, the derivative of x, squared times dx. Now, if the curve is given parametrically in respect of t, like a parametric equation x equal x of t, as an example x equal 3t plus 1, and y is also given in respect of t, then L becomes the integral from a to b, the square root, the derivative of x, dx over dt squared plus dy over dt squared times dt. Arc length calculation practice. Find the length of the following curve from x equals 0 to x equals 4 of y equal 1/3 x to the power 3 half or 3 divided by 2. L is equal to integral from 0 to 4 square root of 1 plus f prime x, the derivative of f, to x squared dx. L equal integral from 0 to 4 square root 1 plus the derivative of fx is 3 divided by 2 times 1/3 of x, 3 divided by 2 minus 1 square dx. L equal integral from 0 to 4 square root 1 plus 1/2 x to the power of 1/2, which is root x square dx, equal integral from 0 to 4 square root of 1 plus 1/4 x dx. If we consider u as being 1 plus 1/4 x, then du becomes 1/4 dx. This cancels out. So dx is 4 du. Then by replacement, L becomes 4 integral of square root of u du, 4 we move it to the outside, which is equal to u to the power of 1/2 becomes u to the power of 3 divided by 2 times 2/3 from the outside. 2/3 is multiplied by 4, so it becomes 8 divided by 3, and u to the power of 3 over 2 is u square root of u. So L equal 8/3, 1 plus 1/4 x. Now we recovered the original value of u. So 1 plus 1/4 x, square root of 1 plus 1/4 x between 4 and 0, which is the final answer here is 8/3 2 square root 2 minus 1. Another example or exercise, let's find the length of the following curve from x equals 0 to x equal pi divided by 4 of y equal ln cosine x. Of course, you can pause the video and try to work it yourself. Now, note something, that the derivative of ln u is du divided by u. And this is u. U is cosine x. So, the derivative of ln cosine x becomes minus sine x divided by cosine x, which is du divided by u, or minus tan x. L equal integral from 0 to pi divided by 4 square root of 1 plus tan square x dx, which is equal secant square x dx, integrated from 0 to pi divided by 4, which is equal ln secant x plus tan x between pi divided by 4 and 0, which is ln square root of 2 plus 1. That's the final answer. Numerical methods for integration. Here in this section, we're going to learn how to approximate a definite integral, which is between two bounds a and b, in order to calculate approximately, this is what approximation means, to calculate approximately its value using different methods such as the direct rectangular method, midpoint, Simpson method, and trapezoidal method. We will start at first with the rectangular or straight rectangular method. So the value of integral for the function fx is the area between the curve and the x-axis on that AB domain. Here what we're going to do is to slice that domain into different rectangles, okay? And for each rectangle we're going to measure its area. That will be, of course, the sum of these areas will be approximately the value for that integral. So to evaluate that area, we divide the domain into n number of slices, each having a width dx, that's the x, and for each slice the upper curve on that tiny domain becomes almost flat as a line, so the area on that small domain can be equated approximately to that of the rectangle of width dx equal b minus a divided by n, which gives you the slice width and the average or approximated height of the curve on that domain. Dx itself is not the problem. However, the choice of the width of dx will define the accuracy of the result, or in other words, the resolution. Because for a larger dx, although you have a faster computation, let's say it is a computer system that is doing that evaluation, but the error margin would be high. But beside of the x, the real problem is choosing the height of the rectangle, because unlike the x below, the height of fx is not a flat ceiling. It changes in respect of y, which is a curve. So we need to pick a value for the height in a way to attempt to get the highest accuracy or highest accurate value for the rectangle or area under the curve for each slice, and thus obtain an overall correct total area under the curve, which is the sum of the slice areas. The choice of the rectangle's height is where each numerical integration method, or most of them at least, differ from the other, whether it was direct rectangle, trapezoidal, midpoint, or Simpson. Simpson also actually uses curve rather than flat lines. Let's start with direct rectangular method. In this approach, we simply use the height of fx for x being the first x bound of each rectangle. So if you look to the right, for each rectangle, you choose the height for that rectangle as being the value of y for the first x, the first edge of this rectangle. Then for the one after it, you choose the height of first x, which is at this point x equal a plus dx. Then for the next one, for this rectangle, fx is f of a plus 2 delta x. Okay, so the height for this rectangle is equal to f of a plus 2 delta x. Now, the formula for that approach is fx equal the sum from I equal 1 to n. Remember, n is the number of slices. fxi, which is the height for the first point of the rectangle, which is for I equal 1, xi is equal to a. So it is the height fxi multiplied by delta x, where delta x is the step, which is equal to b minus a divided by the number of slices. B minus a in this case divided by 3, or this distance over here, the one separating each two consecutive vertical lines, or the width of the rectangle. As a practice, let's solve this problem. Find the area of the following function between x equal 1 and x equal 2 using the straight rect method. The number of slices is equal to 5, and this is the function, which is y equal 1 divided by x. As you notice something, the domain should start at least from x equal 1. Why? Because for x equals 0, this function is not defined, doesn't exist. Actually, it goes to infinity for a vertical asymptote, which is x equal 0. So, solving using this formula, fx equal sigma I equal 1 to n fxi, which is the height of the rectangle at the first point, first edge encountered at each rectangle multiplied by delta x, with delta x is equal to b minus a divided by n. b is 2, that's the second bound, minus a, which is 1, divided by 5, or number of slices. So for each slice, the width is 0.2. Okay, so fx is equal to, remember we have 5 slices. It is 1, because for the first rectangle, we're starting from x equal 1. That's a, the first boundary. Times, for x equal 1, fx is 1 divided by 1, times delta x, which is the constant here. That's the constant multiplier throughout all the areas. So 1 times 0.2 plus 1 over x. The second x is 1 plus 0.2. That's the next rectangle. So we started at 1, then you add up 0.2, which is the edge of the second consecutive rectangle. So 1 divided by 1 plus 0.2, which is 1.2 times 0.2, plus then the next one is 1.2 plus 0.2 times 0.2, then 1 divided by 1, 4, which is the one we ended with in the previous area, okay, in the previous rectangle. You add to it 0.2 to jump to the next rectangle, times 0.2 plus 1 divided by 1.6 plus 0.2. Notice something, which is the last rectangle has a boundary which is 1.8. Because 1.8 plus 0.2 gives you 2, which is the entire boundary. But we are measuring according to the first edge of each rectangle times 0.2. This gives us the value approximated to 0.7456. You will see that it's not pretty accurate. It is fair because the real value, by solving the integral from 1 to 2, would give you 0.693. However, remember that we're measuring according to only 5 slices. That's why you have an error margin here. To calculate the error margin, you subtract the real value from calculated value, and then you divide by the value. It would give you a percentage of the error margin. So fx is equal approximately to 0.7456. Let's check the actual value for the integral. The real value is I equal integral from 1 to 2 of 1 divided by x dx, which is ln x between 2 and 1, ln 2 minus ln 1, of course ln 1 is 0, equals 0.693. That's the real value. So on one hand, this method is not the most accurate. On the other hand, the number of slices is small. This also affects the accuracy. On one hand, it's not the best method. However, the accuracy is affected by the number of slices chosen. That's why you don't have an accurate result. Now let's check the other method to evaluate or approximate the area underneath the curve between two boundaries A and B. What you have here is the method of trapezoid. Okay, as a reminder, how to evaluate the area of a trapezoid. A area is equal 1/2 B1 plus B2, which is the first base plus the second base divided by 2 multiplied by the height. Now in this context, what are the actual bases and the height of the trapezoid? The first base is y1, or the value of fx for the first point. The second y, or the second base, is f of x, for x is equal to the second edge of the trapezoid. In this case, let's say here you have a, y1 is fa, y2 is fa plus delta x, which is f of the second point, the second x right after a, cross a step of delta x, multiplied by h, which is delta x. If you notice underneath, this is how we are evaluating the area under the curve. We are following a trapezoidal pattern. The first base is the first fx for the first x of the rectangle. Second f is for the second point of the rectangle, second edge, and delta x is the height. So the trapezoid rule uses the values of y equal fx, y1 and y2 for both edges of each rectangle, x1 and x2. And it is more accurate than the direct rectangular method in general. Okay, it depends on the number of steps again and shape of the curve. Sometimes the rectangular form or the rectangular method works better. The formula for that fx is equal to sigma I equal to 1 going to n, which is the number of slices, 1/2 fxi, which is the height of the first x, plus fxi plus delta x, which is the value of y for the next x on the rectangle, multiplied by delta x, where delta x is equal to b minus a divided by n, which is the height of the trapezoid in this context. Let's take back the first example and solve this example that we've seen previously using the trapezoidal method. Fx is equal 1 divided by x between x equal 1 and x equal 2, n equal 5, which is the number of steps. Again, fx is equal sigma I equal 1 to n 1/2 fxi plus delta x times delta x, where delta x equal b minus a divided by n, which is 0.2. 2 minus 1 divided by 5. Fx is equal 1/2. The first bound is 1 plus 1, which is 1 divided by x plus 1 divided by 1.2. So 1 divided by 1 fxi plus delta x, which is 1 divided by 1 plus 0.2, which is 1.2, multiplied by 0.2 plus 1/2, 1 divided by the second point, which is, okay, x of the second point starts from 1.2, where the other ends, plus 1 divided by 1.2 plus 0.2, which is 1.4 times 0.2, all the way down, and let's get the answer. So the final answer is 0.695635. Pretty accurate, no? Because the actual value for this integral is around 0.693, and this is only for 5 slices. Notice here, this is the real value by calculating the integral the classical way, 0.693, pretty close. Another method for numerical integration is the midpoint rule. This numerical method works similarly to the rectangular method, straight rectangle, except that the chosen height for that rectangle is actually the value of y equal fx for the midpoint, or for x equal to xi plus xi plus delta x divided by 2. To give you a preview on how it works, so let's say this is a slice from this curve. The height for the rectangle chosen is the value of f. For x is the middle of this interval, which is x plus delta x divided by 2. And as you notice, it has its advantages. Why? Because it truly can hit the nail and get a very accurate result. Why? You would think that we've missed this part, which is underneath the curve, but not counted within the area of the rectangle, the white rectangle over here. However, this excess to the left is around the same value of the triangle, which is to the right, the white triangle. What we've missed here is compensated, is made up for to the left, which makes this method get a highly accurate value. For small, tiny intervals, here you only have 3 intervals. Okay, what can you expect? But for little bit higher number of intervals, you can get a pretty accurate result. In other words, the value of y is the height of the curve for the x value that sits in the middle of each interval, as we mentioned. So what is the formula for that? Fx is equal to sigma I equal 1 to n, which is the number of slices again, the value of f for the midpoint x, which is xi plus delta x, which is the x to the right, correct? Divided by 2 times delta x, which is, of course, b minus a divided by n. Let us take back the first example and solve it again using the midpoint method this time, which is fx equal 1 divided by x between x equal 1 and x equal 2. Also, number of slices is equal to 5. So fx is equal sigma I equal 1 to n f of xi plus delta x divided by 2 multiplied by delta x. Fx is equal to 1 divided by, okay, x should be replaced by xi plus delta x divided by 2, which is, for the first interval, a equal 1, correct? That's a equal 1 plus xi plus delta x, which is 1 plus 0.2 or 1.2 divided by 2. We are replacing x by this value times 0.2 plus 1 divided by the second rectangle, 1.2 plus 1.4 or 1.2 plus 0.2 divided by 2 times 0.2, all of them multiplied by delta x or 0.2. Next one, 1 divided by 1.4, where the other one, the previous one, ends, plus 1.4 plus 0.2 or 1.6 divided by 2, all the way. So the value for that fx is equal to 0.6919, very close to the actual value. Notice something, the real value is 0.693, so it is pretty accurate. And as you increase the number of steps, you can get even a much better value. Simpson's rule or method. Unlike in the previous methods where mostly what is used is the rectangular approach in order to evaluate the area underneath a curve, in Simpson's rule, actually the area is evaluated using a set of polynomial curves spread throughout the interval, just like you see here. It is like to emulate the behavior of the curve itself. Of course, here in this case, the actual formula or the actual approach is a little bit complex, a little bit different, so to speak, than what we've seen previously. What is Simpson's formula? The formula is the following. Fx is equal to delta x divided by 3, this time, multiplied by all of these products, which are respectively fx0 plus 4 fx1. Here x0, x1, x2 are the respective points at each interval, so that's x0, that's x1, x2, etc. at the beginning of each rectangle, so to speak, although we're not using rectangles in this case, plus 2 fx2 plus 4 fx3 plus 2 fx4 to fxn. Only for the first and the last point you don't multiply by neither 4 nor 2. As you notice, you have fx0 not multiplied by anything and fxn at the end not multiplied by anything. But in the middle, for each odd function, meaning for x1, x1 is an odd number, an odd position, an odd index, it is multiplied by 4. Then for x2, multiplied by 2. For x3, which is odd, multiplied by 4. For x4, which is even, multiplied by 2. So how to actually write the formula? At first, so here is how it works. You multiply delta x divided by 3 by the following sequence. For the first and last points, x0 to xn respectively, you evaluate fx0 and fxn without any multiplication. But in the middle, for each even point, you multiply by 2, notice. And for the odd point, you multiply by 4. For the even, you multiply by 2. Alright, only the first and last points, you simply place fx and you sum up everything together. We multiply by delta x divided by 3 eventually. Let's create a more generic formula for Simpson's rule. So what this formula would be, what you see here at first, let's start noticing delta x divided by 3, that's a constant multiplier, it doesn't change. Within this sum, these components, inside the parentheses, fx0 and fxn, both the first and the last components, are not multiplied by anything. What changes is from fx1 to the last element or the one before the last, you have an alternative shift from a multiplication by 4 to multiplication by 2, then 4, then 2, all the way down. This is the pattern we are looking for. Fx is equal to delta x divided by 3, that's constant for everything, multiplied by, also you place fx0 and fxn because they don't change, they are not multiplied by anything, plus the sum from I equal 1 to n minus 1 times fxi multiplied by 2 multiplied by I modulo of 2. Now what is modulo? If I is equal to 1, it is odd, correct? So the odd number divided by 2, it has a remainder of 1, which when you multiply it by 2, it remains. So you get 2 plus 2 or 4 multiplied by fx1. But for I equal 2, which is the next component, notice something here. 2 is divisible by 2. So 2 modulo 2, modulo is the remainder of a division. When you divide 2 by 2, the remainder is 0. So 0 by 2 gives you 0. What remains is the plus 2 here. You multiply it by fx2. Let us again take back the first example of fx equal 1 divided by x between x equal 1, x equal 2, n equal 5. Nothing changed. And we're going to try the Simpson's rule for this equation. fx is equal delta x divided by 3 fx0 plus 4 fx1 plus 2 fx2 plus 4 fx3. So fx is equal 0.2 divided by 3, again the step is 0.2, times 1 divided by 1, which is fx0, okay, the first boundary, or a, plus 4 times 1 divided by 1.2, which is 1 plus 0.2, the second boundary immediately, plus 2 times 1 divided by 1.2 plus 0.2, which is 1.4, plus 4 divided by times 1 divided by 1.4 plus 0.2, which is 1.6, plus finally f of the last x, which is fxn, or 1 divided by 1.6 plus 0.2, 1.8. The first and last are not multiplied by anything. So the answer would be 0.488624. But if you increase the number of slices to, let's say, 1000, you get a value very close, if not almost exactly this value. Okay, so Simpson doesn't work always. It works for a higher resolution, better than other approaches. Now let's talk about improper integral. What is an improper integral? It is a type of integrals where either the interval is infinite, so the interval of integration goes to infinity, just like you see in this example where I equal integral from 0 to infinity, okay, of 1 divided by x squared dx. Now here, not only the interval goes to infinity, where x goes to infinity, but you also have a problem, another problem, that the integral starts from x equals 0, which is undefined. The denominator becomes 0 and you cannot divide by 0. That's another problem. So this example is not only for this type, which is where the interval goes to infinity, or the integral itself goes to infinity, which is also the case here. It has a vertical asymptote. It means that at one value of x, you have no defined values for y. A specific value of x where you have an asymptote. An asymptote is like a barrier, like here, for example. So for 1, we have no problem. But for 0, you are dividing by 0. Okay, 1 divided by root of 0. So this goes to infinity. In other words, for x equals 0, you have no sum, you have no defined values, you have a barrier, which is an asymptote, x equals 0, where the curve approaches plus infinity at x equals 0, but it cannot reach x equals 0. It approaches it, but it can never breach it. This is like a value that is not permitted to cross through. It's an undefined value within the interval. This is what an improper integral means. Either the interval goes to infinity, or you have the value of the integral of the sum itself at one point goes to infinity and is no longer defined. Unlike Riemann's integral, these require solving through limits because they violate the rule of proper integrals. For the upper limit, integral from alpha to plus infinity fx dx, where alpha is a constant well defined on fx and plus infinity is the upper limit going to infinity, it is equal to limit for t goes to plus infinity, integral from alpha to t f of x dx, and we solve it for t, then we find the limit when t goes to plus infinity. For the lower limit, when the lower limit goes to minus infinity, integral from minus infinity to beta, beta being a point well defined on fx, of fx is equal to limit t goes to minus infinity, integral from t to beta f dx, and then we find the limit for t goes to minus infinity after solving the integral for the lower boundary being t. Now for both limits, integral from minus infinity to plus infinity fx dx is equal to limit for t going to minus infinity between gamma and beta fx dx plus limit from t going to minus infinity beta to gamma fx dx, where beta is a point chosen arbitrarily to split the interval. Okay, the integral converges if the limit exists, if it stabilizes at a fixed value, otherwise it diverges and becomes open-ended. Now let's do an exercise. I equal integral from 1 to plus infinity of 1 divided by x squared dx. So we converted to limit from t going to plus infinity, integral from 1 to t, so the upper boundary is replaced by t of 1 over x2 dx. This gives you limit t going to plus infinity from 1, integral from 1 to t, x minus 2 because we moved it to the numerator, so the power should be flipped to a negative sign, dx, which gives us limit from t, for t going to plus infinity, x to power minus 2 plus 1 divided minus 2 plus 1, or x minus 1 divided by minus 1, and the boundaries are from t to 1, okay, or from 1 to t, which gives us, okay, minus 1 over x, boundary between t and 1, or limit for t going to plus infinity, minus 1 over t minus 1 or plus 1. Now let's check, okay, for t going to infinity, this becomes 0, and here you still have plus 1. So I equal limit t going to plus infinity 1 minus 1 over t, which is 1 minus 1 over plus infinity equal 1. So this integral converges to 1. Infinite discontinuity. Infinite discontinuity takes place when the integral becomes undefined or jumping to infinity on one of the edge boundaries or within the interval at one point in the midst of the interval. This discontinuity at a lower limit is called is when fx is discontinuous at a point which is x equal a, where x equal a is a vertical asymptote, just like for the function 1 divided by x. You see, for x equal a, which is 0 equals 0 in such case, you have a jumping or a jump to plus and minus infinity for this curve. So this function is not defined for x equal a. That's why for this integral you cannot solve it properly on this at this point. So you have epsilon, we consider it as a very small number, slightly greater than a in such case. So integral from a to b fx dx, where a is the vertical asymptote and where fx is not defined at x equal a, is equal to limit when epsilon goes to a plus, which is a point slightly greater than a, where you have a definition for the integral from epsilon to b fx dx. Discontinuity at upper limit. Fx is discontinuous at x equal b, where x equal b is a vertical asymptote, so the function is not defined at this point, which is the upper limit for this integral. So in this case, epsilon is a very small number, slightly below b, slightly less than b. Okay, so integral between a and b fx dx is equal in such case to the limit when epsilon goes to b minus, which is the value slightly below b, of integral from a to epsilon fx dx. And the third case, discontinuity at a point within the interval, fx converges only if both limits exist and are finite. Okay, you have a c, which is an arbitrary point chosen between a and b to split the integral, and epsilon is between c minus and c plus. So integral from a to b fx dx is equal to limit epsilon, because here it diverges both at b and a. Okay, so it is equal to limit epsilon goes to c minus for the integral between a and epsilon fx dx, plus limit where epsilon goes to c plus, integral from epsilon to b, okay, fx dx. Exercise integral from 0 to 1 of 1 divided by x to the power of a dx, for a is in R or within the realm of real values. For which values of a does the integral converge? Okay, so here we don't have a problem within the interval itself, but within the integral when using x equals 0, this integral, this sum goes to infinity, okay, because 1 divided by 0 is infinity. So let's check for which values this integral converge. Okay, so this integral from 0 to 1 of 1 divided by x to the power of a dx is equal to limit epsilon goes to 0 plus, and we change 0 here within the boundaries, we flip it by epsilon, where epsilon is a value slightly above 0 of 1 divided by xa dx, equal limit epsilon goes to 0 plus, integral from epsilon to 1, x to the power of minus a dx, because we moved it from the denominator to the numerator. Okay, so I equal, or the integral is equal to limit epsilon going to 0 plus of x minus a plus 1. Here we solve the integral. As you remember, we add 1 to the power, and then this power we divide by it the entire thing. Okay, so x to the power minus 8 plus 1 over divided over minus a plus 1 between 1 and epsilon. Then okay, so this is equal to 1 to the power 1 minus a minus epsilon to the power 1 minus a. And of course, since 1 divided by 1 minus a is a constant, you move it outside of the limit. Okay, it is a constant. So it is equal to limit epsilon going to 0 plus 1 to the power 1 minus a minus epsilon 1 minus a. Okay, and there's no problem of keeping 1 minus a underneath the limit as well. So here, anything to the power, or when you have 1 to the power of anything, this gives you simply 1. So I equal limit epsilon going to 0 plus of 1 minus epsilon to the power 1 minus a divided by 1 minus a. As a reminder, anything in the power of 1, so anything placed in the power of number 1 would give you back 1. Okay, so it doesn't matter what we have in the power of the value of 1. 1 to the power of n, whatever n is within the realm of real values, it gives you back 1. Now let's go through the scenarios. So if 1 minus a is less than 0, then a is greater than 1. What happens in such case? You have the limit epsilon going to 0 plus of 1 divided by 1 minus a. Here we broken down the fraction. We separated 1 and epsilon 1 minus a. So limit epsilon going to 0 plus of 1 divided by 1 minus a minus 1 divided by epsilon a minus 1 multiplied by 1 minus a. So what happened here is you had in the numerator epsilon 1 minus a. A is greater than 1, so you have a negative power at epsilon. So you need to bring it down. Once you bring it down, you flip the sign of the power. Epsilon 1 minus a becomes actually epsilon of plus a minus 1. And remember that this is a 0 value. It is near 0 multiplied by 1 minus a. And here also in the denominator, since a is greater than 1, so you have a negative sign multiplied by epsilon a minus 1. Negative in the denominator and negative right before it, you multiply them together, it gives you a positive value. The limit epsilon going to 0 plus of 1 divided by 1 minus a minus 1 divided by 0 plus, which is epsilon, and you have a negative sign behind it because a is greater than 1. This gives you limit epsilon going to 0 plus of 1 divided by 1 minus a minus 1 divided by 0 plus, and since a is greater than 1 and it is negative, then the denominator is negative, minus multiplied by minus gives you plus 1 divided by 0 plus, which is plus infinity, so the limit diverges in such case. As a preview on what that would look like, let's suppose that a is greater than 1, which is a equal 2 specifically. So I equal limit epsilon going to 0 plus of 1 minus e to the power minus 1 divided by 1 minus 2. So this is the limit of minus 1 times 1 minus epsilon to the power of minus 1, which is minus 1 plus 1 over epsilon. Since epsilon goes to 0 plus, so this is plus infinity. Minus 1 doesn't count, so it diverges to plus infinity. If 1 minus a equals 0, then a equal to 1. So let's solve it for a equal to 1. That's integral from 0 to 1. 1 divided by x dx is equal to ln x between 1 and 0. ln 1 is equal to 0 minus ln 0, which is minus infinity. So it goes to plus infinity. In such case, for a equal 1, I diverges to plus infinity. Now for 1 minus a greater than 0, then a is less than 1. In this case, epsilon of 1 minus a goes to 0. Why? Because in such case, this epsilon has a positive power, so it remains in the numerator and it goes to 0. So I equal limit of epsilon going to 0 plus of 1 minus epsilon to the power of 1 minus a divided by 1 minus a, okay, which is equal to 1 divided by 1 minus a, since this quantity here, epsilon, is 0. So in such case, the limit converges to 1 divided by 1 minus a. Then I converges to 1 divided by 1 minus a only for a less than 1. So how to study an integral like I equal integral from a to plus infinity fx gx dx when it is not solvable? This converges according to Dirichlet. These are called Dirichlet's conditions. When fx is monotonic and decreasing gradually to 0 as x goes to plus infinity, that's one of the products, then gx also at the same time has a bounded total variation on a to plus infinity. In other words, integral in absolute value, integral from a to x gt dt is always less than or equal to m for all x greater than or equal to a. Dirichlet's test guarantees only a conditional convergence. Absolute convergence is when integral from a to plus infinity of fx gx in absolute value dx is equal to 0. Okay, this is when this entire sum converges as well. This is when we call it an absolute convergence. In other words, integral from a to plus infinity of fx gx in absolute value dx is always less than plus infinity, plus or minus infinity. So as a practice for that, you have integral from 1 to plus infinity of cosine x divided by x dx. Alright, now we cannot solve this integral using elementary function, okay? Let fx be 1 divided by x and gx be the other component of the integral, which is cosine x. Now you notice that fx decreases to 0 gradually as x goes to plus infinity, okay? So 1 over x decays gradually and rapidly to plus 0, or when x goes to plus infinity. As for gx, it varies between 0 and 1 because it is a cosine value, okay? So whatever x is equal to a value which is greater than or equal to 1, cosine x varies between 0 and 1. It keeps oscillating. So integral between 1 and plus infinity cosine x dx is equal to sine x between plus infinity and 1. Here we are getting the sum of each function apart, okay? So we took that of gx. This is equal to sine x between plus infinity and 1. It is always greater than equal to 0 and less than equal to 1 from 1 to plus infinity. Now this satisfies Dirichlet's conditions. This integral oscillates and is bounded. It goes to 0 as x goes to plus infinity for 1 over x. 1 over x is decreasing, and cosine x oscillates and is bounded between two values which are 0 and 1. Gx, let's consider the limit of cosine x dx for t goes to plus infinity between 1 and t. It is equal to limit t goes to plus infinity of sine t minus sine 1, correct? Which is always, so gx in absolute value is always less than or equal to 1 plus sine 1. So gx is bounded by this total variation. Now cosine x in absolute value is often greater than or equal to 1 divided by 2 on infinitely many intervals. So we can use 1 divided by 2 as the lower bound of the integral. Let xn, which is the angle, be equal to 2 pi n. because this is how it varies, okay? And delta is a very small number around xn. So this is true for whatever xn is in the interval xn minus delta and xn plus delta. So delta is a very small number which is very close to xn, whether from the positive side or the negative side. So cosine x in absolute value, as we mentioned, is greater than or equal to 1 divided by 2. You multiply that by 1 divided by x on both sides, so you get cosine x divided by x greater than or equal to 1 divided by 2x. So before proceeding any further, let us talk about the midpoint rule for integration. For a small interval between a and b, the integral is actually the area, okay, from a to b underneath the curve or between the curve and the x-axis. Now, usually for a very tiny interval, this is equivalent with a very small error margin to the area of the rectangle from a to b being the width, so the width is b minus a, and multiplied by the height or like the midpoint height of the curve for the midpoint rule, meaning that it is the height of the curve or the value of y for x equal xm, which is xm is the middle point. It is equal to b plus a or a plus b divided by 2. Okay, and if you notice to the left, so you have a part of the rectangle covering an area which is above the curve. However, this will make up for the area, okay, which is below the curve but outside of the rectangle. So by approximation, the area covered by the rectangle which is above the curve, which is an excess, is equal to the area that has been missed underneath the curve, which is not included within the rectangle. So the midpoint rule or the midpoint integration is equal to f of the midpoint x, so the value of f or y, which is the height of the curve, at x equal a plus b divided by 2, which is the value for the midpoint x in f, times b minus a, which is the width of the rectangle. This gives you the area of the rectangle or the area of the curve, the approximated area of the curve between a and b, which is the value of the integral for fx dx between a and b. So going back to our exercise, you have cosine x divided by x, an absolute value greater than or equal to 1 divided by 2x. For a small interval, the midpoint rule for integration is integral from a to b fx dx is equal f a plus b divided by 2 times b minus a. Okay, which is xn plus delta, that's the first bound, and xn minus delta divided or times 1 divided by 2x dx is equal to 1 divided by 2 times xn plus delta plus xn minus delta divided by 2. So we are applying this rule, okay, a plus b divided by 2, replacing x, times b minus a, which is xn plus delta, the upper bound, minus xn minus delta, the lower bound. So if you evaluate it, you have 2xn in the denominator and 2 factors out because you have a division by 2. Delta is eliminated, so it is 1 divided by 2xn times xn minus xn 0 and delta minus delta, which is 2 delta. So it is 2 delta divided by xn. So I equal 1 divided by xn times 2 delta. The value for this integral, you can sum it up from 0 to plus infinity for n of 1 divided by xn times 2 delta. So xn again is equal to 2 pi n. You replace xn by 2 pi n, you have the sum from 0 to plus infinity of 2 delta divided by 2 pi n, which is equal to delta over pi and sigma from 0 to plus infinity of 1 divided by n. And this is a harmonic series, okay, that keeps diverging to plus infinity as n approaches to 0. Why? Because 1 divided by 0 is plus infinity, so it's not absolutely convergent. Finding the convergence of I equal sum from 0 to 1 of sine 1 divided by x divided by square root of x dx, oscillatory blow up, a very famous, a very common type of problems. So I equal limit from epsilon going to 0 plus integral of sine or sin 1 divided by x divided by square root of x dx to 0 plus, the bounds of the integral are epsilon to 1. Of course, you notice that 0 is forbidden in the denominator. It is not defined for the function, and also in the numerator where you have a division by x as well. At first, sine 1 divided by x is bounded and has a maximum of 1 and a minimum of -1. Okay, so sine is an oscillatory function, but however it has bounds between 1 and -1, as 1 divided by x goes to infinity, of course, when x goes to 0. So sine is bounded. Now, for 1 divided by x, it goes to infinity as x goes to 0. So we must treat the integral as improper, of course. Let's find if this integral absolutely converges. Now, at first, we know that the maximum absolute value for sinus of 1 divided by x as x goes to infinity is +1. Okay? That's the maximum for sine 1 divided by x. Given that prerequisite condition, or given that premise rather, we can replace sine 1 divided by x by 1 since the maximum is 1. Alright, and we can place it back in the integral. So it is equal to integral from 0 to 1 of 1 divided by square root of x dx. As we mentioned, we've converted sine 1 divided by x by 1. We've replaced it by 1. So the integral, if we solve it normally, it becomes square root of x is x to the power of 1/2. You move it upwards to the numerator, it becomes x to the power of -1/2. -1 over 2. You add to it +1, and then you divide by -1 over 2 plus 1. Okay, just as we integrated previously any type of power, which is equal to 2 multiplied by x to the power of 1/2, which is square root of x, between 1 and 0, which is equal to 2 square root of 1 minus 2 square root of 0 equal 2. As a conclusion, I converges absolutely at 2. Checking the convergence of I equal integral from 0 to plus infinity e minus x ln x dx. Here in this integral we have a problem both in the bound that is lower, which is x equals 0 because ln 0 goes to minus infinity, and ln plus infinity goes to also plus infinity. So let's split the integral at a convenient value like x equal 1, since this sum seems to diverge at both the lower and the upper bounds. I equal integral from 0 to plus infinity e minus x ln x dx is equal to integral from 0 to 1 e minus x ln x dx, which is the first part, we will call it a, plus integral from 1 to plus infinity e minus x ln x dx. Let's study the convergence for a. So it is integral from 0 to 1 e minus x ln x dx for x equal 0. Now, for x equals 0, e minus x goes to 1 because exponential of 0 is 1, just like anything placed to the power of 0. However, ln x or ln 0 goes to minus infinity, so it is divergent. For x equal 1, e to the power of minus 1 is equal to 1 over e, and ln x goes to 0, so it is convergent. For the second part, which is b, for x equal to 1, again you have e to the power minus x goes to 1 divided by e, and ln 1 goes to 0. So the integral converges at x equal 1. Okay? Now, for x goes to plus infinity, you have e to the power of minus infinity equal to 0, but ln x goes to plus infinity. So e to the power of minus infinity goes to 0. Multiplied by plus infinity, it goes to 0. So the integral converges at x goes to 0 plus, at x goes to 1. Thus the integral absolutely converges. Now, for the purpose of the next problem, we're going to review the equation of a circle. Let's say you have a circle of center M of coordinates a and b respectively, x and y of the center of this circle, and radius r. The equation of this circle would be x minus a squared plus y minus b squared equal r squared. Of course, when you have a circle centered around the origin, which is O, 0, 0, the equation becomes x squared plus y squared equal to r squared. As an example, you have x minus 1 squared plus y minus 0 squared equal 4. So the center here is M that has x equal 1, okay, y equals 0, so it is sitting on the x-axis, but it is shifted by 1 to the right, and the radius is square root of 4, which is 2, okay, according to the equation, r squared here to the right of the equality. So r squared equal 4, then r equal 2, so the radius for this circle is 2. The equation becomes, of course, we need to find it in respect of y. So y equals square root of 4 minus x minus 1 squared, or in other words, fx equal of square root 4 minus x minus 1 squared. This is what you work on when working the integral or other calculation according to y in respect of x. As an example, let's find the area underneath the circle between 3 and 5. So you have a circle here, and you can easily find the equation of that circle because the center is M, defined at x equals 3 and y equals 0. So a equals 3 within the equation you've seen before. And the radius for that circle is 2, which is 5 minus 3. So y equal square root of 4 minus x minus 3 squared. You can easily find it out by looking at the previous slide. Let u be equal to x minus 3. du equal dx. Here we are changing the variables. Okay, so x minus 3, we placed it as u. du equal dx. Of course, we need to change x, or which is the boundaries for that integral need to be changed. Okay, before we did not do that because we used to restore what u looked like before into the integral. Here we may not get back into what u used to be. Okay, so we may not restore the value of u as being x minus 3. That's why we are converting everything to u. This includes the boundaries of this integral. So x is between 3 and 5. u is equal x minus 3, correct? So u then is between 3 minus 3, okay, which is for x equals 3 minus 3, that's 0, and 5 minus 3. So you place the different boundaries within this equation to get where u is varying. What are the boundaries of u? So u is in 0, 2, because for x equals 3, for x equals 3, u is equal to 0. For x equal 5, u is equal to 2. Then the integral becomes I equal sum from 0 to 2 square root of 4 minus u squared du. So we converted the domain into I equal square root of 4 minus u squared du, and from x to u. So between 3 and 5 became from 0 to 2. Now again, another conversion. Since it is a circle, we need to use polar coordinates, which are x equal r cosine theta, y equal r sine theta. So let's suppose u is equal to r cosine theta. We are changing variables. Of course, r equal 2. Then du equal minus r sine theta d theta. Then, so since u equal 2 cosine theta, then theta equal r cosine, or cosine to the power of minus 1 of u divided by 2. Here we also need again to change the interval. So u that used to be in 0, 2 has to move into theta. Now theta is equal r cosine u divided by 2, which is cosine minus 1 to the power minus 1, 0 divided by 2, or cosine 0, and cosine minus 1, 2 divided by 2, which is cosine to the power minus 1 of 1. So theta is in the interval. Okay, So what gives us 0? Which angle? It is cosine of pi over 2. So the angle is pi over 2. And the angle that gives us cosine 1 is actually 0, because cosine 0 is equal to 1. Hence, I is equal to integral from pi over 2 up to 0 of the square root 4 minus u square. U is equal to 2 cosine square theta, so it is minus 4 cosine square theta, times du, which is minus r sine theta d theta, or minus 2 sine theta d theta. I equal to integral between pi over up to 0 of 2 square root of 1 minus cosine square theta, because 4 can be factored out and the square root of 4 is 2, so you place it outside of the square root, times minus 2 sine theta d theta. Then you remove 2 from both of the products, and it is minus 2 times 2, which is minus 4. You place it outside of the integral. Of course, 1 minus cosine square theta is sine square theta. The square root for that gives you sine theta. You multiply it by the other theta, you see? Okay, so square root of sine square theta times sine theta gives you back sine square theta d theta. Of course, multiplied by minus 4 on the outside. What is sine square theta? It is actually 1 minus cosine 2 theta divided by 2 d theta, which is given in trigonometry, because as you see, and I'm gonna place the equations on top so as to make you figure out how to get from sine squared theta back to 1 minus cosine 2 theta divided by 2. So I equal minus 4 integral from pi over 2 to 0, 1 minus cosine 2 theta divided by 2 d theta. You move this 1 over 2 outside of the integral, so you divide minus 4 by 2, you get minus 2 integral from pi over 2 up to 0 of 1 minus cosine 2 theta d theta, which is equal to minus 2 on the outside multiplied by theta minus 1 divided by 2 sine 2 theta, which is the integral of cosine 2 theta between 0 and pi over 2, which gives us, for theta equals 0, everything cancels out. For theta equal pi over 2, and remember you have a minus in the middle, minus pi over 2 minus 1 half sine 2 pi over 2, which is sine pi. Okay, this also cancels out. What remains is I equal minus 2 multiplied by minus pi over 2, which is equal to plus pi. Actually, this is the area for the quarter of a disk, okay? Because the area, the actual area is 4 pi, which is pi r equal to, so 4 pi divided by 4 gives you plus pi. This is correct given that the area of a circle with radius r equal to is pi r square equal pi 2 square equal 4 pi. So the area of 1 quarter, which we have here, is 1 over 4 times 4 pi, which is plus pi. The same answer, that's the area of the disk underneath the circle from 3 to 5, which is a quarter of one disk. That's everything for this section. Thank you for watching.